Hard grind, the epic journey of the world's biggest tunnel boring machine. On April 4, the world's largest tunnel boring machine broke through to the open air after almost 4 years underground. Called Bertha, the giant digger was tasked with the challenge of building a tunnel large enough to carry 4 lanes of motor traffic under the heart of Seattle. The story of how it made the 1.7 miles, 2.7 kilometers, journey under the skyscrapers of the port city is not only a tale of a remarkable machine, but also of civil engineering, geology, politics, luck, and proving the old adage that anything that can go wrong, will. Bertha's journey started not in Seattle, but in Nisqually, Washington, about 60 miles, 100 kilometers, south of Seattle. On February 28, 2001 at 10:54 a.m., the rural community was the epicenter of a magnitude 6.8 earthquake that rocked the region. Now known as the Nisqually or Ash Wednesday earthquake, the tremors wreaked havoc on the cities and suburbs to the north. In Seattle, about 400 people were injured in the quake and 1 person died of a heart attack. Meanwhile, the brick facades of older buildings shattered and rained down on cars in the street, and many places of business were evacuated for fear of ruptured gas lines. Though the traffic system was paralyzed by people trying to get home and the landlines and mobile networks were jammed, most places got off lucky with little more than knocked over furniture, and cans and boxes strewn on shop floors. But one thing that was hit hard by the quake was the area's infrastructure. Inspections showed that most of the bridges in the Seattle area were inadequate to withstand another such tremor, and a crash program was initiated to retrofit all the bridge piers with concrete sleeves as reinforcement. It was expensive, but it seems to have done the job, with one exception, the Alaska Way Viaduct. A fixture of the Seattle waterfront since the 1950s, the viaduct was a 2-tier elevated roadway that is one of the major north-south arteries of the city, carrying tens of thousands of commuters and goods lorries each day on a scenic route along the waterfront. It had suffered a moderate amount of damage in the quake, but engineers assessed that there was no point in making the extensive repairs needed because the structure was too dangerous. The basic design was too light and, instead of sitting on a solid foundation, the support pier sat in a bed of alluvial redeposit soil. Though the worst was repaired, the experts concluded that another earthquake could cause the viaduct to pancake, as happened in 1995's Great Hanshin earthquake in Japan. The question was not whether to tear it down, but when and what to replace it with. What followed was almost 8 years of debate, deliberation, hearings, and flat-out arguments. Some people wanted to replace the old viaduct with a new one to keep things as they were. Others felt that the viaduct cut off the historic waterfront from the rest of the city and turned the area under it into a gloomy underworld. Some advocated replacing it with a cut-and-cover tunnel. Others wanted a surface-level roadway. And the unabashedly anti-motor car types wanted the viaduct torn down and not replaced at all. In all, over 90 proposals were looked at, but in January 2009 the state and city governments announced a new project by the Washington State Department of Transportation, SDOT, and Seattle Tunnel Partners, a partnership of Spain's Dragados and Tutor Perini in the U.S. In this, the viaduct would be demolished and north and south stretches of State Route 99 would be reconnected by a $3.1 billion tunnel that would run away from the waterfront, the line of the viaduct, and the Battery Street tunnel that linked the viaduct and the north end of the roadway. The tunnel would run under the city center at a depth of 200 feet, 61 meters, to avoid a forest of pilings, cables and pipes from some 160 buildings above. Meanwhile, the waterfront's sea-wall, which was also inadequate, would be rebuilt and strengthened. This latter project was a tricky job in itself because the area is made up largely of redeposited soil from harbor dredging and is the home of several historic warehouse piers that are now major tourist attractions, the Seattle Aquarium, an active ferry port, a hotel, and a cruise ship terminal. It was thought that the tunnel would be least disruptive. All this may sound straightforward enough, but to replace a roadway with as much traffic as SR 99 carried on a daily basis with a deep tunnel was unprecedented. It was not only deep, but the plan was for it to be 1.7 miles, 2.7 kilometers, long, and wide enough to hold a 2-lane double-decker road, ventilation and firefighting equipment, and an emergency pedestrian walkway concealed in one wall. Put all that together and the engineers soon realized that they would need a tunnel boring machine, TBM, and not just any tunnel boring machine. They needed to have one specially built, and it would be the biggest one in the world, Bertha. TBMs are actually not that new. The first one was built by the famous engineer Sir Mark Kingdom Brunel in 1825 to dig the Thames Tunnel at Wapping in London. Along with Thomas Cochrane, Brunel invented a machine that was basically a giant iron can, called a shield, turned on its side with one end open. The closed end is pressed into the digging end of the tunnel and consists of rows of small doors where workmen remove the soil using picks and shovels. Meanwhile, the shield held up the tunnel walls. When enough was dug out, the doors were closed and jacks were used to push the shield forward and the walls were sealed with brickwork. Over the next century, these machines became more sophisticated as power was added alongside drills and rotating digging heads. They eventually became common tunnel excavators and were used on projects like the Channel Tunnel across the English Channel, Japan's Seikan Tunnel from Honshu to Hokkaido, Switzerland's Gotthard-based tunnel, and the Crossrail Tunnel under London. Bertha, named after Seattle's first woman mayor, Bertha is what is known as a soft rock TBM, as opposed to a hard rock TBM. The latter, as the name suggests, is essentially a big rock drill designed to bore through solid granite or something equally nasty. That's not to say that Bertha had an easy time of things. Far from it. Soft rock TBMs have to contest with sand, which can be as damaging to machinery as rock, as well as gravel, clay, loam, and the odd boulder or other surprises. Bertha had a particularly hard time because the Seattle area was formed hundreds of thousands of years ago by a series of glaciers pushing to and fro during the Great Ice Ages. This pushed up massive hills of debris made of 8 different kinds of soil under the city center. In fact, the soils are so varied that across the face of the digging machine the soil types could vary radically. Worse, the line of the new tunnel runs from the waterfront, where Bertha was below the waterline, up under the city through 10 distinct geological zones to come out of a hillside, where the soil is bone dry. It also didn't help that after a century and a half of building, Seattle is a warren of foundations, pilings, cellars, sewage lines, railway tunnels, road tunnels, and pedestrian tunnels. And then there's the famous underground city that was buried and built upon after a fire devastated the city in the 19th century. Even before tunneling began, old deposits of fill soils had to be removed and areas strengthened to withstand the passage of the TBM. To create a machine that was large enough for the job, Hitachi Zosen Sakai Works in Osaka, Japan was selected from a list of 5 candidate firms to design and build the 57-foot diameter, 17.4 meters, mechanical behemoth. Because it weighs in at 6,664 tons, 6,559 tons, it wasn't possible to ship Bertha across the Pacific in one piece, so after testing it was disassembled and shipped to Seattle, where it arrived in April 2013 and was put back together again at the bottom of an 80-foot, 24.3 meter, deep, concrete-lined pit on the waterfront in the shadow of the viaduct. How it works when put back together. Those invited New Atlas and other members of the media to tour inside Bertha, and that in itself is an indication of just how large it is. Most digging machines are things you look at from the outside, but the Seattle TBM is so large that it's like a cross between a gigantic locomotive and a cylindrical factory 322 feet, 98.2 meters, long. Instead of a solid piece of machinery, it's filled with catwalks, ladders, and stairs. It even has a control room inside, as well as a pair of break rooms. Remarkably, despite its size, Bertha is largely automated and only needed about 25 people to operate it at any one time. Inside the control room in Bertha Cutterhead, the working head of Bertha is the cutterhead, which completely covers the front of the machine. It weighs a massive 2,132 tons, 2,000 tons, and is covered with 260 steel teeth designed to break up soft soil and guide it through gaps inside the cutterhead, or grind up large boulders. Many even rotate to be replaced by other, different teeth as the job requires. This is turned by a 25,000 bhp, 18,600 kilowatts, electrical system and allows the cutter head to rotate at up to 1.2 revolutions per minute, and the machine moves forward at a speed of about 35 feet, 10 meters, per day. One key factor when digging is the presence or absence of water. Depending on how you look at it, they can both be a blessing or a curse. On the one hand, having water in the soil ahead makes it easier to cut through and move, so if there isn't enough, Bertha is able to inject water and a soapy conditioner into the soil to break it up into a soft paste. But if there's too much, the cutter head ends up ineffectual, churning a load of liquid mud without going anywhere. Detail of a rock cutter. In addition, that excavated soil slurry must be made to go only where it's wanted. To do this, the cutter head is pressurized to up to 5.6 atmospheres. This helps to force the slurry to stay in the cutter head until it's removed, but it's a fine balancing act. The machine maintains a constant pressure on the trapped soil. If there's too little, the slurry just churns inside the cutter head and the front face of the tunnel could fall in. Too much and the machine is pushing a wave of slurry ahead of itself. One unpleasant aspect of the pressure system is when the cutter head needs servicing. Pressure must be maintained at all times, so when a tooth is worn out or a boulder needs shifting, the workers have to take on the role of deep-sea diver and pass through an airlock to work inside a pressurized bubble of air inside the cutter head. The slurry pipe directly behind the cutter head inside the machine is the slurry pipe. This is a steel tube about 3 feet, 1 meter, in diameter that has a very important function. Without it, the slurry coming from the cutter head would blast into the digging machine with 5 atmospheres of pressure behind it. Instead, the pressure is reduced until the slurry can pass safely through it, impelled by an Archimedean screw onto a conveyor belt, which sends the soil back to the end of the tunnel and out to a waiting barge on a nearby pier. This expandable conveyor is joined by thousands of feet of cables and pipes to supply Bertha with power, water, conditioner, and other essentials. The shield. The front part of Bertha is covered by the shield. As with Brunel's original machine, this is a cylindrical hull that holds up the sides of the tunnel wall and protects the machinery and workers from muck and water. It also allows the TBM to move forward. As it bores, Bertha crawls like an inchworm with the shield creeping forward and the rest of the TBM rolling up behind. Bertha. Before launch, inside the backroom are 56 hydraulic jacks forming a ring inside the shield that push it forward as the machine cuts by pressing against the reinforced concrete walls that line the already bored section of tunnel. This wall is made of 2 foot, 0.6 meter, thick concrete panels or segments. The rams push against the forwardmost ring of panels and inches forward like a worm. In addition, there are other jacks used to align and steer the shield. The lining rings are made of 10 concrete panels, with each ring weighing 360,000 pounds, 163,000 kilograms, lined with rubber gaskets to keep water out. Some panels are shorter than the standard size to allow the tunnel to curve in certain sections to allow it to go left, right, up, or down. Behind each panel is forced grouting to stabilize the tunnel. One interesting thing about the lining panels is that they are not laid by hand, but by a pair of robotic erector arms that collect the panels from an electric tram and place them precisely against the inner wall of the steel shield in a staggered pattern. Having 2 arms allows Bertha to lay down panels twice as fast as other machines. As the shield moves forward, the grouting is injected into the exposed gap where the steel once was, and the process continues. Based on previous motorway tunnel borings in Spain, this gap is designed to be as small as possible to improve stability. Control room. Also inside the shield is the control room, where the workers monitor Bertha's systems by computer, guide it, look out for signs of earth shifting unexpectedly, or if too large a boulder is encountered that might have to be broken up by hand. Behind this is the break room, which might seem like a luxury unless you remember that by the time the digging was completed, the walk back for lunch would have been almost 2 miles. Trailing gear. If the shield is Bertha's head, then the trailing gear is the digestion system, articulated and resting on massive rollers. The 300 feet, 91.4 meters, of girders and gear contain the machinery to supply the TBM with grout and grease. In its intricate interior are the pumps and ventilation equipment as well as restrooms, a kitchen for the crew, and a rear control room to handle the section's operations. It's also where the liner sections are collected from a small electric railway car called a segment transport truck and moved forward for placement. Bertha's tale. Bertha digs in on July 30, 2013, under the eyes and cameras of the international media. Bertha powered up, the cutter head started rotating, and the TBM started its career in a cloud of white dust as it cut into the cement plug on the north end of its containment pit. It was expected to emerge on the other side of the city center in 14 months, and by 2015 the project was due to be completed. It seemed as if the actual tunnel digging was nothing but a formality leading up to the cliched and anticlimactic ribbon cutting, but it turned out that Bertha had more than rock and clay to dig through. It also had to go through a lot of unknowns to get to its goal, and some of those bit back hard. Dust kicks up as Bertha hits concrete. One of the big unknowns for the project was the geology. Though the entire route had been studied and core samples drilled, the soils ahead of Bertha were remarkably complex, and this was especially true at the start, where large areas are made up of redeposited soils from dredging and construction. And speaking of construction, there were fears about the effect of the largest tunnel boring machine in history chewing its way under any number of skyscrapers. This meant that Bertha was much more closely monitored than if it was cutting through a mountain in the middle of nowhere. In addition to the usual laser surveying and the other aids for making sure that Bertha broke out at its destination within a couple of inches, the engineers rigged the buildings along the route with sensors to record any signs of vibrations or the foundation shifting. However, another big unknown was Bertha itself. It was a one-of-a-kind, which means that its one and only field test was the job itself. Even though Dot admitted that there was a bit of a learning curve as the machine dug into the earth. Exactly how it would perform and how to handle it couldn't be sorted out beforehand. Bertha shuts down. Then in December 2013, the unknowns came together in a cocktail of failures that almost doomed the whole project. On December 3, the TBM shut itself down after traveling 1,083 feet, 330 meters, and it struck a steel pipe that the Seattle Times newspaper said was used by WSDOT engineers to measure groundwater and had been left behind by mistake. Then on December 6, things really got bad. The rubber seals around the main bearing failed and grit got into the workings, resulting in broken parts and damaged gears as the TBM overheated alarmingly. Whether this was due to hitting the pipe or due to design flaws is still part of a legal dispute between WSDOT and the contractors, but the upshot was that after several attempts to move, by February, Bertha was trapped 120 feet, 37 meters, underground with no way to back out. Repairing Bertha a month later, Hitachi concluded that the only way to repair Bertha was to dig it out and partly dismantle it. In other words, to save a major engineering project would mean starting another major engineering project. To repair the TBM would mean sinking a 120-foot deep, concrete-lined shaft ahead of Bertha in an area of unstable waterlogged soils, coax the boring machine forward into the pit, lift out the 2,000-ton cutterhead, partly dismantle the machinery, replace a large percentage with redesigned parts, put it all back together, test it, rebury the whole thing, and then resume digging. All this while dealing with mounting costs, union problems, political battles, lawsuits, and demands to shut down the project completely and leave Bertha where it was forever. It was simple, like the Normandy invasion. Bertha in the repair pit. Watch, VR flying simulator. Birdly lets you fly like a bird between NYC skyscrapers. Play video. Play unmute. Current time 0 o'clock, duration time 2:09. Loaded, 0% progress. 0% full screen. VR flying simulator. Birdly lets you fly like a bird between NYC skyscrapers. One of the advantages of tunneling under a city is that it avoids that bane of the contractor, archaeology. Many places have strict environmental regulations to protect archaeological sites or to make sure that they are properly surveyed and excavated before being disturbed. That was fine as far as Bertha was concerned until it became necessary to dig the rescue pit. The area where the pit was set for digging included historical pits that had been excavated and then refilled. Now there not only had to be more geological survey holes drilled to get a detailed picture of the soil, but 60 test holes had to be dug to look for artifacts. Fortunately, nothing significant was found. More significant were the long delays caused by the breakdown. It turned out that the damage to Bertha was much more extensive than originally thought, and there were all manner of lawsuits between those and the contractors over who should pay for what in regard to repairs and delays, lawsuits that are still ongoing. Equally significant were the delays caused by digging the rescue pit. Because the area was so waterlogged, engineers had to drill holes and pump water out of the ground. Otherwise the earth would have collapsed in on itself like a soggy cake. It's a standard procedure, but not in such a built-up area, and in December 2014 a large crack appeared in a road in the historic Pioneer Square district. Fearing that the pumping operations were causing a sinkhole to open up, work was again delayed as new surveys conducted and countermeasures implemented. Bertha's shield being dismantled finally, on February 19, 2015. Bertha cut through the concrete plug in the repair pit after being coaxed up to it at minimum speed and power under the watchful eyes of Hitachi engineers. It took 2 days to cut through the plug itself, but without overheating or stalling. It took a few more days to clear the pit of debris and move the front of the machine onto a pair of giant skids. Meanwhile, at the top of the pit, a giant traveling crane capable of lifting 4 million pounds, 1,800 tons, waited to lift the cutter head and other components out for repairs and replacement. Since Bertha was considerably larger than, for example, an MG midget, and much of the shield had to be cut away with torches, the repairs took until December 2015. This ended up involving hauling out the cutter head in one piece to refurbish it and replace many of the cutters, putting in new gears, installing a redesigned main bearing as well as new seals, electric cables, hydraulic lines, pumps, and control systems. Not to mention putting back all the bits taken out to get at the damaged parts and re-welding the shield back into place. Once all of this was done and running tests were completed, the repair pit was filled in with sand, capped, and the water pumps were turned off to allow the water table to reassert itself. Shortly before Christmas that year, Bertha started to move forward. Bertha undergoing post-repair tests, it seemed as if the worst was behind, but in January 2016, as Bertha tunneled through a layer of stiff clay mixed with sand and gravel at a depth of about 120 to 150 feet, 37 meters to 46 meters, under the fragile viaduct, another sinkhole opened up 100 feet, 30 meters, behind the TBM, causing another shutdown for 6 weeks as 250 yards of concrete and soil were injected into the hole to stabilize it. More serious was the political fallout as recriminations shot about regarding over-excavation of soil, demands for more aggressive procedures to stabilize the earth around the tunnel, and renewed calls to abandon the project altogether. And there were more arguments over who should compensate who for the delays. At this point, one almost expected someone to sue himself. Bertha digs again despite all of this bickering. Digging resumed on April 29, 2016 in a very public fashion. Despite being almost 200 feet, 61 meters, underground, the residents of Seattle were well aware of what was going on because the viaduct, which was still in use, was shut down for a fortnight as a safety precaution. When you tell 100,000 commuters that they have to find another way to get to work, it gets noticed. Fortunately, no damage was caused by Bertha's passing and the route was reopened in May. After that, Bertha dug deep under the city center and the chances of affecting anything on the surface grew more and more remote. For the next 11 months, the TBM tunneled away without incident with occasional stops for inspections and maintenance. As it dug, the machine passed through many different layers of soil and the water table was eventually left behind. To compensate, Bertha started squirting water jets in front of the cutter, as well as foams and conditioners to break up the soil. Meanwhile, the usual arguments about money, schedules, insurance, and who was at fault over the initial breakdown continued between the state and the contractors. Breakthrough then, after a final 6-inch course correction in March 2017, Bertha was at the end of its long and controversial journey. On April 4, after over 2 years of delays, the giant drill cut through the concrete plug at the reception pit built for it at 6th Avenue North and Thomas Street near the present SR 99 route. With suitable drama, The great machine ground its way through the plug, sending up clouds of dust as water jetted out and huge chunks of cement and rebar crashed into the pit as the press looked on. Dust erupts as Bertha breaks free. It was an historic event, but history is not very kind to the likes of Bertha. It's a one-of-a-kind machine built to carry out only one specific job. Perhaps it would have been nice to put it in some extremely large museum, but it's also a very valuable piece of equipment, too valuable to let sit idle. The end of Bertha instead. Bertha is currently being dismantled in the pit at the north end of the tunnel, which will afterwards become part of the ramp connecting with the motorway. The cutter head and shield are being cut up into pieces smaller than 20 tons, 18 tons, so they can be taken away by road, and most of the steel used to build the machine will be taken to a local iron foundry to be melted down to build the fittings inside the tunnel. As for the motors, pumps, electronics, and the rest, they will be sold back to Hitachi. Meanwhile, work will shift to the inside of the tunnel to build the double two-lane decks that will carry cars north and south. The seams of the lining need to be minutely inspected, electrical systems need to be installed, firefighting apparatus fitted, and the ventilation brought online. There will even be a system of variable signage that can be altered to suit present traffic and road conditions. If all goes to plan, the tunnel will open to traffic in 2019, 2 years and over $200 million outside of plan. Bertha being dismantled. So what can we take away from the story of Bertha? Having been inside it and personally witnessed both the start and the end of its tunneling career, I can confidently say that it is the most remarkable big machine I've ever seen that didn't float and didn't have a propeller at one end. Built in the wake of a natural disaster, it shows that we don't live in an age of make do and mend, and that thinking big isn't something left behind in the 20th century. Bertha is also a lesson in humility. It shows that in civil engineering, like in war, the plan only lasts until the first shot is fired and that the supreme law is Murphy's Law. Things break, money runs out, bureaucrats bicker, and even the most well-intentioned projects can come to nothing. Near Lake Washington on the opposite side of Seattle from where Bertha broke through are the famous ramps to nowhere, which are left over from an expansion of the WA 520 motorway that was never completed. More than once, Bertha came close to joining them. But the most significant lesson of Bertha is the irony of how even the most heroic engineering achievements can become utterly invisible. People may gawp at the Eiffel Tower or the Empire State Building, but they also pass without a second glance the scores of magnificent bridges left by Isambard Kingdom Brunel across Britain or the intricate system of locks and dams that keep the basins of the Mississippi and Missouri rivers from flooding yearly. Bertha from behind, that's what Bertha's legacy is. According to those when the SR-99 tunnel is completed, it will seamlessly integrate with the roadway and motorists won't know where it begins or ends. Nor will they be aware of the fact that they're speeding along hundreds of feet underground or all the technology that makes it possible. All they'll know is that the tunnel cuts a half hour off their journey and ask themselves, is it really worth the toll charge the state slapped on to use it? And, perhaps, that's how it should be. The most successful technology is the one you take for granted. The video below shows Bertha's last moves under its own power. For more details on the SR-99 project, visit